Okay, as I look at this, ladies and gentlemen, it says, using the data below, calculate the delta S sub 0 for the following reactions. Well, S and S sub 0 is the standard entropy. Okay, most of the time, we're going to use our thermodynamic data table. So go ahead and take your thermodynamic data table out. For this particular one, we will not use it. Why? Because we are given values for entropy with the problem. So we are going to be using the values that we have been given. Now, when I am counting my change in entropy, okay, as I'm counting my change in entropy, I need to remember the following. And folks, this is one of the biggest problems that I have seen in entrance slips this year. All right? Change in entropy is equal to the entropy of, let me do it in different colors, the entropy of the products minus the entropy of the reactants. So it is entropy of the products minus entropy of the reactants. Well, let's go back up here. We did our products in green, our reactants in blue. What are my products? Do I have products? No, I have a product. So here is my product. Here are my reactants. So, don't just add things up in the order that they are on your balanced chemical equation. That is not the way it happens. Products minus reactants. So, what I'm going to do is I'm going to first do my products in green down here. So, chromium 3 oxide is my product. And how many are made? 2 of them, right? That is important. That is important because when I'm doing my calculation down here, I take 81.2, which is the value for chromium 3 oxide. But remember that there are 2 of them. So I have to multiply that by 2. Then I'm going to subtract my reactants. Now I'm going to put a big bracket on here because my reactants are 4 chromium and 3 oxygen, right? 4 chromium, 3 oxygen. So I'm going to take 4 times the value of chromium, 23.77. And to that, I'm going to add, what did I say, 3 oxygen? Yeah. 3 times the 205.138. So that is, oh, I got to close my big bracket. So that is what I need to do to calculate my entropy. That's what I need to do to calculate my entropy. Does everyone understand where I got the 2, the 3, and the 4 that I put in front of the values? Does everybody understand where I got the 2, the 3, and the 4? It came from the coefficients in the balanced chemical equation. Up here, the 2, the 4, the 3. That's where I got those values. So when I do my math, I'm just going to simply take 81.2, multiply it by 2, and I get a value of 162.4. I'm going to subtract that from my bracket is 4 times 23.77, 95.08 plus 205.138, 615.414. So once again, 162, I'm done with that part, minus, I'm going to add those two together, and I get 710.494. So I'm going to take 162.4, and I'm going to subtract. So my new value now for my entropy, my change in entropy is equal to negative 548.094. I need to have a label on this, so I come back up to my original right here. My change in entropy is going to be joules per Kelvin times mole. That'll be right on your data table. So my label is joules per Kelvin times mole. So my final answer here for my change in entropy is negative 548.94. If I were going to sig fig this, okay, if I were going to sig fig this, ladies and gentlemen, you have to remember that we are adding and subtracting, correct? So our adding, subtracting do not take the specific number of significant figures, but we do what? We look at the closest to the decimal point. So for this particular one, I'm looking at here, here, and here. Which one is closer? The 2, right? So I've got 10th, I've got 100th, I've got 1000th. So be the most correct, I'm going to round that to the 10th, which would be negative 548.1. Huh? I think I shut sig figs off. I think I shut sig figs off on this. Yeah. Delta. That's a delta. That's a triangle.
No, I'm saying like all the other stuff. You have the triangle, an S, and then a circle. Like in the videos. I don't know why.
Oh, the sub-zero?
Yeah.
That just means standard.
Okay.
Okay. Craddock? I have not done that. Okay, the question was, if I have an unbalanced equation, do I need to balance it? Absolutely. I haven't given one like that yet, but I would always check to make sure it was balanced. Okay, I would always check to make sure it's balanced, but I'm not trying to fool you like that. All right, I'm not trying to fool you like that. Now, let me ask you this. In terms of my reaction, I said that my change in my entropy was negative 548.1. So am I getting more ordered or less ordered? More ordered, right? I'm getting more ordered because my entropy is disorder, correct? And it is going down. Now, if you would look up here, based on my just based on my knowledge that I have 2 reactants and I have 1 product, does that seem to me that it's getting more ordered? Yes. Okay. What states are most ordered? Solids. Here I have a solid and a gas going to a solid, right? So that leads to me, just eyeballing it before I even start, leads to me, looks like that's getting a little more ordered. So my entropy is probably going to go down, which in fact it did. Okay, go ahead and copy the second example, and then we will work it. Okay, it says calculate the standard entropy change for the following reaction at 25 degrees Celsius. 4 aluminum solids plus 3 molecules of oxygen gas will yield 2 aluminum oxides in the solid form. Now, does what state it is in matter? Does what state it's in matter? Absolutely. Because if you look at your data table, they have different things. They have solids, they have liquids, they have gases. All right, so the state matters. Now, if I'm just eyeballing this in, does it look like I'm getting more order or more disorder? Looks like I'm getting more order. Why would you say more order? Okay, who can explain to me why this is more ordered, other than Tyler and Connor? Andrew? It's a solid and a gas, and it's becoming 1 solid. So I have 1 product compared to 2 reactants. That should give me a little hint. I have a solid and a gas going to just a solid. That gives me a little hint, too. So what I need to do is I need to read on my data table my values. So what I usually do for these is I just put those values right above them. So I look at aluminum oxide as a solid, and I got 51.00. Would you agree? Find that on your data table. We're on the entropy column, the S column, which is the 3rd one, right? That's another place where people get stuff wrong. They take numbers from wrong columns and work them with different things. What is my entropy for aluminum as a solid? I got 28.32. Would you agree? Now, my final one I've got to get is my entropy of oxygen. It's O2 as a gas, and that is 205.0. Agreed? So now I have my values. I need to go ahead and calculate them. Well, I know, like I said before, my delta S, my change in my entropy, is equal to my products. And I have 2 of the aluminum oxide minus the entropy of my reactants. I have 4 of the 28.32 plus 3 of the 205, and big bracket that. So, looks to me like that is going to be what? 102 minus 28.32 times 4 gives me 113.28. plus 205 times 3 gives me 615. My bracket's closed. So then I take 102 and I minus 615 plus 113, and that gives me 728.28. So my change in entropy is 102.00 minus the 728.28, and I get a value of negative 626.28. Now let's look at sig figs. What am I going to do for sig figs here? I'm going to round it to the 10th because I have 100th, 10th, 100th, correct? So I'm going to round this to the 10th. So that's going to take that to 3. What's my label going to be? Well, look at my column on my data table. What's the label on that column on the data table? Now, I predicted that I would be decreasing my entropy. Is that what happened? Yeah, that's what happened. That's what happened. So that's a pretty good prediction. I was right on with that one. Okay. Now, what I want you to do is I want you to do this on your own. Okay? Do this one on your own. I'm going to work it on my own. When you are finished with this, just let it sit out. I'm going to come around and check to see how you're doing.